Focus today is increasing output and reducing defects. USB port assembly improvement plan for Barata Corporation. Barata's charging box assembly line is experiencing USB port alignment defects that are creating rework, slowing delivery, and affecting customer satisfaction. The recommendation is a practical improvement plan using Lean and Six Sigma to reduce defects, improve output, and make the process easier to follow. Rada is dealing with two problems at the same time, a quality problem and a production flow problem. USD alignment defects are currently at 20%. That means that about one out of every five charging boxes is failing because of this issue. That is a significant amount of rework and it directly affects production speed and customer satisfaction. The pilot goal is to reduce the defect rate to less than 5%. That gives Barada a clear improvement target while still keeping the pilot realistic. A controlled pilot using Lean and Six Sigma is the recommended next step. Lean addresses wasted motion, delays, and rework. Six Sigma addresses defects, variation, and process control. Together they fit the problem well. The leadership decision needed is approval for a controlled pilot that reduces USB orientation defects, shortens rework, and improves output without turning the issue into a blame exercise. The issue does not appear to be a technician effort problem. It appears to be a process problem. The current workflow depends too much on what employees are expected to already know. The briefing will move through what is failing, why Lean and Six Sigma fit, what should change, and what leadership would need to approve. The defect is showing up during testing, but the real problem starts earlier in assembly. The basic workflow moves from the order window to gathering parts and tools, to assembly, to testing, and then to shipping. That sequence sounds straightforward, but one critical detail is not being controlled early enough. The issue is circuit card orientation. The instructions do not clearly state that the A connectors should line up with the 2.0 side and the B connectors should line up with the 3.0 side. That detail really matters because the test results make the problem visible. The 2.0 connectors should test at 240 megahertz. The 3.0 connectors should test at 2.5 gigahertz. When the circuit card is reversed, the boxes test in reverse. The larger leadership concern is timing. By the time testing catches the defect, more labor has already been added. At that point, the company is not just correcting an error, it is losing production capacity that could have gone toward new work. The bottom line is that assumed knowledge creates process risk. When a critical step is only understood informally, the process is easier to get wrong. Barada can lower that risk by making the correction orientation clear, visible, and checked before the product reaches final testing. Lean and Six Sigma fit this situation because Barada is not dealing with only one issue. There is wasted movement in the process, and there is also measurable defect problem. On the Lean side, the technician moves from the workstation to several different areas, including the order window, incoming area, stock area, tool area, and outgoing area. Some of that movement may feel normal because it is built into the routine, but it still adds time. Repeated walking is hidden cycle time. It keeps the technician busy, but it does not add value to the product. That is where Lean can help. Lean focuses on reducing waste, including unnecessary motion, delays, and rework. Six Sigma is needed because the defect rate is measurable and high. A 20% USB orientation defect rate shows that the process is not producing consistent result. DMAIC gives Barada a structured way to fix the issue without guessing. In the define phase, the problem is defined as excessive USB orientation defects and inefficient assembly flow. In the measure phase, baseline data should be collected, including defect rate, first pass yield, cycle time, rework time, and delivery performance. In the analyze phase, root causes should be identified. Likely causes will include unclear instructions, similar looking circuit card decides, no in-process checks, and testing that catches the problem too late. In the improvement phase, changes can be tested, including workstation organization, visual instructions, orientation checks, and mistake proofing. In the control phase, the process should be monitored to make sure the improvement holds. The pilot should be judged by practical measures: fewer defects, better first pass yield, shorter cycle time, less rework, and improved delivery performance. The solution does not need to be complicated. Barada needs to make the correct process easier to follow and harder to get wrong. The first recommendation is to stage tools and materials closer to the workstation. The technician should not have to keep leaving the workstation for the number 1 Phillips screwdriver, lid insert tool, screws, or component kits. The second recommendation is point of use kitting. The right kits and screws should be ready before assembly begins, especially for larger orders. That creates a more consistent starting point and reduces extra movement. The third recommendation is visual work instruction. This is one of the most important changes. The workstation should include a photo, diagram, or color-coded example showing the correct circuit card orientation. The key instruction needs to be obvious. A connects to the 2.0 side and B connects to the 3.0 side. The fourth recommendation is an in-process check. The orientation should be checked before the lid is installed. If something is wrong, the technician can catch it early instead of finding it after more labor has been already gone into the product. The fifth recommendation is mistake proofing. Barada should consider a fixture, guide, or design control that prevents the circuit card from being installed backward. That is better than relying on reminders because it helps stop the mistake before it even happens. Together, these changes organize the work, make the correct orientation visible, and move quality control earlier in the process. For this to work, leadership has to reinforce the new process. The process improvement will not last just because it is written down. It has to be supported in the actual work area. The decision needed is to approve one controlled pilot area, assign a supervisor owner, and allow daily review of output, defects, and rework. The expected value is straightforward. Less rework, better first pass yield, shorter cycle time, and faster movement of customer orders. To sustain the improvement, Barada should use standard work documents, training, supervisor checks, and technician feedback. The people doing the work need to be a part of the feedback loop because they will usually see process problems first. Right now, the process is reactive. The defect is found late, rework is added, and delivery slows down. The pilot moves the control point earlier. The correction orientation becomes visible, the check happens before the lid is installed, and defects are prevented before they move further downstream. The recommended action is to start small, measure honestly, and scale only what proves value. That approach protects quality output and customer delivery without overcomplicating the process. Barada's issue is not just a defect issue, it's a process design issue. By using Lean to improve flow and Six Sigma to reduce variation, Barada can create a clearer, more reliable assembly process. Thank you.